Right now, there are bridges carrying thousands of speeding cars, massive trucks, and millions of pounds of steel, while secretly moving beneath them, not breaking, moving. And if those bridges stopped moving for even a moment, some of them would literally tear themselves apart. Most people think bridges survive because they're unbelievably strong, but strength alone is not enough, because bridges face a problem most people never think about. They are under attack every second of every day. Wind twists them, traffic shakes them, heat expands them, cold shrinks them, earthquakes ripple through them, and all that stress builds silently for decades. So how do these giant structures survive without cracking in half? The answer involves hidden movement, giant cables under impossible tension, and engineering lessons written in disaster. Because humanity learned the hard way what happens when bridges fight physics instead of working with it. A bridge looks solid, permanent, like a giant piece of frozen steel and concrete. But structurally, it's alive with force. The second a truck rolls onto a bridge, the structure reacts instantly. The roadway bends slightly downward. Support beams stretch. Pressure shifts through the entire structure. Some areas get squeezed, others get pulled apart. F equals May. And unlike buildings, bridges deal with moving weight. That makes everything harder. A skyscraper mostly carries static load. Bridges carry constantly changing force. 1 second the bridge is empty. The next second, dozens of heavy vehicles hit it at once. And the pressure isn't only vertical. Wind pushes bridges sideways. Storms create vibration. Even temperature changes become dangerous. On very hot days, large steel bridges can physically expand by several feet, then shrink again when temperatures drop. Imagine building something enormous while knowing it will constantly grow and shrink for decades. Now add time. Millions of vehicles crossing every year create tiny stress movements over and over again. And small repeated stress is dangerous, because structures rarely fail all at once in the beginning. They weaken quietly. Tiny cracks form deep inside steel. Concrete slowly fatigues. Bolts loosen microscopically. Most people never see any of it happening, until suddenly, the damage becomes visible, and hidden stress once caused one of the most terrifying bridge failures in history. A bridge that literally started twisting itself apart in the wind, in front of everyone watching. In 1940, the Tacoma Narrows Bridge opened in Washington State. At first it looked beautiful, long, elegant, modern. But almost immediately, something felt wrong. The bridge moved constantly in the wind. Drivers reported waves rolling through the roadway. Cars bounced. The deck twisted unnaturally. People actually nicknamed it Galloping Gertie. At first it seemed funny. Then the wind hit at exactly the wrong rhythm. The bridge began oscillating violently, not because the wind was insanely powerful, but because the movement kept feeding itself. Each gust added more energy. The twisting got worse. Steel cables snapped. The roadway tore apart section by section. Then the entire bridge collapsed into the water below. The terrifying part, it wasn't overloaded. There was no earthquake, no explosion. The bridge destroyed itself because engineers underestimated movement. That disaster completely changed how bridges are designed, because engineers realized something critical. Bridges don't survive by staying rigid. They survive by controlling movement safely. So how do modern bridges survive forces powerful enough to destroy earlier designs? The answer starts with a strange idea. The strongest bridges on Earth are designed to bend on purpose. This sounds backwards at first. People trust rigid things. We assume movement means weakness. But in engineering, controlled flexibility is often what prevents disaster. Nature figured this out long ago. Look at trees during storms. Rigid trees snap. Flexible trees bend and survive. Modern bridges use the same principle. When heavy weight pushes downward, engineers want certain parts of the bridge to flex slightly, not too much, just enough to spread the force safely across the structure. Because if a bridge refuses to move at all, stress builds up in concentrated areas. Eventually, something cracks. Flexibility acts like a pressure release system. The bridge absorbs energy instead of fighting it directly. That's why giant suspension bridges can visibly sway during storms. Some move several feet sideways in strong wind. Passengers often don't even notice, because the movement is smooth, controlled, expected. And to make this possible, engineers carefully balance two opposite forces: compression and tension. Compression squeezes materials together. Tension pulls them apart. Concrete is excellent under compression. Steel is excellent under tension. So modern bridges combine both strategically. One material resisting crushing force, the other resisting pulling force. The entire structure working like a giant balancing act. Every part helping distribute stress away from dangerous weak points. But the craziest part of bridge engineering is hanging high above some of the biggest bridges on Earth. Thousands of steel cables, quietly carrying the weight of entire highways. Look at a suspension bridge like the Golden Gate Bridge. Most people focus on the towers, but the real magic is in the cables. Those massive curved cables are under incredible tension every second. They're constantly being stretched by the weight of the roadway hanging below, and steel is unbelievably good at handling tension. The weight from the bridge deck transfers upward into vertical cables, then into the giant main cables, then down into enormous anchor points buried deep underground. The bridge is essentially hanging in the air. That's why suspension bridges can span huge distances without collapsing under their own weight. Instead of forcing the roadway to support itself rigidly across the gap, the cables distribute the force across the entire system. And those cables are insanely strong. Some major bridge cables contain tens of thousands of individual steel wires bundled together. If laid end to end, they could stretch around Earth multiple times. But cables alone aren't enough, because wind creates another nightmare. At large scales, air itself becomes dangerous. Strong crosswinds can push bridges sideways, create twisting motion, or trigger violent oscillations like Tacoma Narrows. So modern bridges are carefully shaped to control airflow. Some have open sections allowing wind to pass through. Others use aerodynamic deck designs that reduce turbulence. Every curve matters, because invisible air can become powerful enough to destroy steel. But even if a bridge survives traffic, storms, vibration, and enormous weight, there's still another enemy engineers fight constantly: time. Because bridges are slowly aging every single second. Bridges don't usually fail from one massive event. Most failures begin invisibly. Tiny cracks, rust hidden deep inside joints, water slowly weakening steel, concrete expanding and shrinking through seasons. One of the biggest dangers is fatigue. Even small, repeated stress can eventually destroy strong materials. Take a paperclip. Bend it once, nothing happens. Bend it back and forth enough times, it snaps. Bridges experience the same thing over millions of load cycles. That's why modern bridges are packed with hidden monitoring systems. Sensors constantly track vibration, movement, temperature, and stress. Some bridges even use AI systems to detect unusual structural behavior before humans notice any visible damage. Engineers inspect cables using magnetic scanning systems capable of finding internal damage hidden inside steel. Drones inspect areas humans can't safely reach. Some bridges are continuously repainted because corrosion never truly stops. The battle against nature is permanent, and sometimes engineers intentionally overbuild certain sections, not because they expect failure tomorrow, but because they know decades of tiny stress will slowly weaken everything. A bridge is never truly finished. It's constantly being repaired, monitored, and protected for its entire life. Because the moment maintenance stops, time starts winning. And strangely enough, some of the smartest bridge designs on Earth aren't built around preventing failure completely. They're built around surviving failure safely. This is one of the most important ideas in modern engineering. Engineers know no structure lasts forever, so instead of pretending failure is impossible, they prepare for it. Modern bridges use redundancy, meaning multiple systems share the load together. If one section weakens, other sections temporarily absorb the force. Some bridge joints are designed to deform before catastrophic collapse happens. Others redistribute weight automatically across the structure. The goal is buying time. Time for inspection, time for repairs, time to prevent a chain reaction. Because catastrophic collapse usually happens when force can no longer spread safely through the structure, and engineers obsess over stopping that chain reaction before it starts. That's why modern bridge engineering isn't really about making bridges indestructible. It's about making them adaptable, flexible, predictable, repairable, and survivable under stress. So next time you drive across a giant bridge, remember what's actually happening beneath you. Steel stretching under tension, concrete compressing under pressure, massive cables quietly carrying impossible weight, wind pushing sideways, heat expanding entire sections, tiny vibrations rippling through the structure every second. And somehow, through all that chaos, the bridge holds. Not because it's perfectly rigid, but because engineers learned something nature understood long ago. The strongest structures aren't the ones that never move. They're the ones that know how to bend without breaking. Subscribe because the next video breaks down what really happens when an airplane gets struck by lightning at 35,000 feet, and why passengers usually never realize how close they came to disaster.